All right, so on the video that was posted, I know there's some camera angle issues and some of the resolution, but the major things that were covered in that video that I'm going to make the assumption that you watched and kind of got a introduction to was going to be the definitions of different acids and bases, and those can also be read in the text to clarify any of those. What constitutes a strong acid, strong base? This should be General Chemistry 1. We should remember that list as it pertains to hydroxides and as it pertains to the 6 strong acids that are generally referenced in this course. Also, I brought up the idea of Kw, which is the equilibrium constant of the autoionization of water, which is water turning into hydronium, H3O plus, and hydroxide, and how Kw and pH are related, which was a part of that video. We also, in the video, talked about conjugate acid, conjugate base, and we talked about using Ka and Kb and what those are. Remember, Ka and Kb are still equilibrium constants. They are just specific to acid-base equilibrium. They are structured the same as Keq and Kc that we've been working with, but they're just a couple little small things that can make these problems a little bit easier for us when we move into the Ka and Kb, because we have to consider water, but water is not in the expression. So what I like to do to start off with is to walk through a couple of these questions on the in-class worksheet. Over the course of going through these questions, I want to touch on each of these as well, and please, ask the questions, stop if you are not clear, because we have a little bit of time today where I'm not lecturing, I'm actually going through how to work these problems out, which is what I'm seeing was an issue, at least somewhat in the last exam, was just how step by step I'm working these out, and you get a chance to see it here versus on the workout Wednesday. So the first question it asks is that, generally speaking, an acid is a compound that blank the pH in solution. So what does an acid do to the pH in an aqueous solution? An acid should decrease. It should lower the pH or decrease the pH in aqueous solution. Now, how does an acid do that? It does that by dissociating to form hydronium. The dissociation of HA creates hydronium, and the anion A, for this case, which is just the generic A, the anion, which is in fact the conjugate base. So dissociating to form the hydronium ion and conjugate base. So it should be, the blanks in there should be decreased, dissociating to form hydronium ion and a conjugate base. Technically, you can answer that and say form negative ion and conjugate acid. That would be technically correct, but the focus here is just using the language. Hydronium, getting in a habit of using this language and understanding. Second question asks about, generally speaking, a base is a compound that should then do the opposite of an acid, so we should be seeing an increase or raise the pH in solution by dissociating to form the hydroxide ion and a conjugate acid. So if we have some kind of base plus water, we generally end up with Hb plus OH minus. So the hydroxide ion and the conjugate acid, Hb. Again, these are the generic equations associated with acid and base equilibrium, right? When we talk acid-base equilibrium, what you should be familiar with is that the Keq for this reaction is products, H3O plus, A minus, over reactants, HA and H2O. But if we looked at the phases on this, we should remember that nothing that is a pure solid or liquid should be included in KEQ. So this KEQ is incorrect because water is a pure liquid. So we should not have water. Even though it is a reactant, we should not have water. And the main reason for that is because in a amount of water, we're talking millions and millions of molecules of water, the change in the water for this is not going to be enough, really, to make an impact. So that's the practical approach. The other reason is that just because we told you, don't put pure liquid. So water is not involved in KEQ, and this is effectively Ka. Why? Because we have an acid dissociation. So we have products over HA. And that's going to always be the case for any acid. Particularly our weak acids, right? Because we know strong acids from Gen Chem 1, we are not worried about equilibrium in strong acids because there is a reverse, right? Let me make sure I write double arrows because we're dealing with equilibrium. With strong acids and bases, pH equals concentration of the acid or base, right? Straightforward. Now with the base, we have a KEQ that is equal to HB plus OH minus and the concentration of base, and this is considered KB. So KC, KEQ is the exact same thing here. We do not have a pure liquid water, but we list them as Ka and Kb. So moving forward, when you see Ka and Kb, particularly the same way that you see the equilibrium constants written on this reference material, you will be given this reference material for quizzes and exams, right? So this will be a reference material. This is not your copy. There is a copy in reference materials in D2L. We're going to just use these for the assessment until I get some laminated. Okay, so this is just a generic recap of what was talked about. Kw is a function of water, right, which we don't really need to talk too much about, but pH is a function of hydronium concentration or hydroxide concentration. We should remember from Gen Chem 1, pH equals negative log of H3O plus. This is also, I think, on your reference material, right? POH is equal to negative log of hydroxide concentration. Again, this is all, this at least is review. This is review. The conjugate as conjugate base can be kind of determined here. Remember, the conjugate acid is the acid that is formed, and the conjugate base is the base that is formed. Here is Ca, Cb. You have to be able to recognize all of these. Base, acid in this scenario, conjugate acid, conjugate base. Acid base in this scenario, conjugate acid, conjugate base. Notice that water can do both. That is essentially the beauty of water, is that it can be an acid and base depending on the environment. Because the auto-ionization of water has a value. If that value, Ka or Kb, is larger or smaller, it will tell you what water will do in that scenario. So we're going to take a look at some of those examples as well. Okay, so let's take a look at a. Let me see if there's some decent left markers up here. Let's take a look at the problem that I listed. And this problem, again, I'm going to always try to incorporate integrative practices from way back, understanding concentration, understanding equilibrium, and using all of these. So, and I've given you kind of a step-by-step in the problem. Notice that in our assessments, I may not give you determine equilibrium expression. I might not give you the instructions, right? I might ask you just the question. Give me concentration. Give me pH. But in this case, we're going to go step by step. So propionic acid with water and write the reaction. So for question 3, propionic acid with water, we can go to our reference material to get the structure. And propionic acid is HC3H5O2. So we have HC3H5O2. This is going to be considered aqueous plus water gives us the conjugate, which is without the proton, C3H5O2, aqueous. It should be negatively charged, plus hydronium, H3O plus. Now, this is very simple. I do not, honestly, it's going to really pain me on assessments when you can't write this equation, because that shows me General Chemistry 1, foundations are not there, and your understanding of how acids, bases, and what they do is not there either. When you see an H written in front for purposes of Gen Chem 1 and 2, this is almost always an acid. That's why we write the H in front, because we could write this C3H6O2. It will still be the exact same. But that H in the front lets you know it's an acid. What is an acid? A donator of a proton. What is a proton? H plus. One way to look at it. If you know that, and if you know that an acid must create hydronium ion, you know an H has to get added to water. I need to see the reaction. If you're not doing that, then you obviously aren't trying. Obviously aren't trying. Okay, so here's the reaction. We got phases. The reaction is balanced. For the majority of what we're going to see, I would say it's going to be 1-to-1, but there are examples of mono and diprotic, and in some cases triprotic acids. We'll try to incorporate those, but we need to set this foundation first before we get into the more complex. So I've told you that 68 grams was dissolved in 300 mils of water at 25 Celsius. Determine the concentration. So this is Gen Chem 1 again. 68 grams in 300 mils. So 68 grams, to get number of moles, we need to calculate the molar mass. That can be done via calculator. 6.06 plus 32 plus 4.01 times 3, 74.09. And then divided by 300 milliliters, which is 0.3 liters. Therefore, we are dealing with a molarity, 68 divided by 74.09 divided by 0.3. We got 3.06. 3.06 molar. All right, so that's the question of part B. Now, I've broken this up, but realize that if you've been given a mass of any acid, a mass of any salt, a mass of anything, you're going to need to convert it to moles. That's just a chemistry thing. That's, again, Gen Chem 1. Once you have that mass, you need to convert to moles. Then, if you know the volume, then you need to convert it to concentration. Determine the equilibrium expression and set up the ice table for this reaction. So, the equilibrium expression is Ka is equal to concentration of the conjugate, C3H5O2, times hydronium all over the acid itself, C3H5O2. Any questions thus far? This is very straightforward. We're starting with the simple stuff. We have left out water. Once again, I should not see you putting in water. You just got to remember that. This is transitioning from chapter 15 to 16, because in 15, we've been working with mostly situations that are gaseous or some aqueous situations where we don't have to worry about leaving any out. We worry about leaving solids out, but in this case, pure water does not involve itself in the expression. Now, setting up the ice table. The ice table involves, and I'm going to do generic just because, HA, H2O, A minus in this case, plus H3O. Realize that HA and A minus are conjugates of propionic acid, or propionate, properly described as propionate, and HA is propionic acid. So the ice table is initial change equilibrium. Our initial value for HA is given to us by the calculation. So let's say I didn't give you the instructions to calculate concentration. Hopefully you'll be able to understand and know that initial here is always in molarity. Therefore, this needs to be calculated. So we have initial 3.06. Remember, H2O, we don't care about. So you'll normally see me write these little dashes. H2O is not involved in the equilibrium expression, therefore we are not concerned with the values in that column. So you normally see me write just a dash, or you may see people cross out that entire column. Now, at time 0, if we were thinking about this from a perspective of after we added it, at time 0, there are no products, right? There's no reaction. That's the main thing that people get tripped up on. They say, well, initially mixed. Initial is always at time 0. Now the change, since all of these is 1 to 1 to 1 to 1, the change is always going to be associated with just X, and for the products it will be plus X, for the reactants, right, minus X. And therefore, at equilibrium, we are dealing with 3.06 minus X, X, and X. If you can get to this point for all the different situations that we're dealing with, then you've done all of the chemical work. Everything else from here is mathematics, for the most part. This is the chemistry of acid-base. Can you write the reaction? Can you calculate concentration? Can you write the expression, fill in the ice table? Everything else from here is math. Okay? Now that you have Ka, you can plug in the values from equilibrium into Ka, and you end up with Ka is equal to X times X over 3.06 minus X. Now, something I talked about in a video is something that can be incorporated into acid-base equilibrium at this point. Up until this point, I've been asking you to determine X using quadratic equation or using graphing function in the calculator. When we're dealing with acid-base equilibrium, particularly for weak acids, right? If we look up the value of Ka in our reference material, that value is 1.3 e to the negative 5. So we got 1.3 times 10 to the negative 5. Remember, these K's do not have units. They're equilibrium value. So if Ka is less than 1, then we know it is a weak acid, right? We know that equilibrium lies to the left. We know that we should still have more reactants than products. But if we take a look and compare Ka to our starting concentration, we can determine whether or not we can drop X. So the definition says that if concentration of HA over Ka is greater than 500, then you can drop the minus X in HA minus X. You can drop the X, meaning you can get rid of it. If you really quickly plug that in, and if you have any math intuition, you know that it's much greater. But 3.06 divided by 1.3 e to the negative 5 gives you 200,000, okay? What that means is that the magnitude of dissociation, essentially the amount of acid that is actually formed in this reaction as a function of the identity of the acid we're dealing with, the magnitude is so small that it will not impact this number effectively. So that goes back to the question we had about the homework. If this is greater than 500, you can drop X. And very rarely will you see situations that it's not. I don't even think that I give too many examples where you see that it's not. Almost always you can drop X. So because of that, now Ka is equal to X times X over 3.06. And now, given our value, we can solve without having to do any quadratic. So it makes the math simple. Now we end up with X squared. So we end up with X squared equals Ka times 3.06. Therefore, X is equal to square root of Ka 3.06. Square root of 1.3 e to the negative 5 times 3.06. Looks like 0.0063. So X is equal to 0.0063 molar, or 6.3 times 10 to the negative 3, right? Okay, so I have asked you, now I've done the work beyond that because I'm answering D. At this point, I'm answering D, where D asks you to calculate the pH. X is not the pH. X is equal to what? Concentration of hydronium, which is what we need to calculate pH. So X is going to be equal to H3O plus, and if we know our pH equation, pH is then equal to negative log of hydronium, which is equal to negative log of 6.3 times 10 to the negative 3, and now we see what our pH should be. Now, should it be greater or less than 7? It should be less than 7. That is how we can double check whether we've done some math right or wrong. Answer is 2.20. So we have an acidic solution. Once we dissolve that much propionic acid into water, deionized water. So that is acid taken all the way through step by step. If you were given this problem, realize that this is just one way to ask this question. You can ask plenty of different questions. So on the next example, I'm going to give some of the another approach. Now, how does this impact all of this? So let's talk about conjugates. This is the conjugate base. This is the conjugate acid. Okay. Are we dealing with a weak acid or a weak base? We know we're dealing with a weak acid because we've been given a Ka that is small, right? Smaller than 1. Therefore, we have a weak acid. We do not have complete dissociation, right? We only have partial. And then you can also look at percent dissociation. And this is a little aside, but if you ever see questions that talk about percent dissociation is the concentration of hydronium over the concentration of the acid, which in this case is 6.3 times 10 to the negative 3, all over 3.06 and times 100, of course. And we see that this percentage is still extremely minuscule, right? .2%, so 0.21% dissociation, right? So we're dealing with less than 1% of your acid is actually dissociated. Less than 1% of the hydrogen proton is being transferred over to water, right? Now, let me see if you can understand and apply this concept. Does the percent dissociation and the Ka, how are they related? So do they have a direct relationship or inverse relationship? increase one, does the other one go down? If you increase one, does the other one go up? See, that's the kind of understanding that you need to use from an application standpoint. That's the kind of question I'm going to ask you. Do you expect the percent dissociation to go up if the Ka goes up? Yes, right. So Ka is directly related to this because as you increase the amount of products, you increase percent dissociation. And the increase in amount of products is what K increases, right? Products over reactants. Products over reactants. Any question about this question? Clarifications needed. This is crawling, right? Then you gotta walk, then you gotta get a tricycle, then you gotta get on a motorcycle. But you don't have to ride a motorcycle until test time. But this is about as simple as a problem you can get right there. So you gotta be able to do this. Okay. So let's take a look at the next example. The next example is a base. So dimethylamine and water reaction. So if we look at dimethylamine, CH3,2NH. So we have CH3,2NH aqueous plus water liquid gives us CH3NH2 plus OH minus. All right, again, this is directly from the reference material. That's where I got the structure from. Notice now when we're dealing with base, you have to create a conjugate acid with the base itself, Ca, and then create the conjugate base in this case, which is hydroxide, right? Hydroxide. Now notice that the N is where the H goes, right? Now notice I wrote it like that. You could write it however you want to, but understand that this comes from understanding structure. Now, based on that first exam and some of these questions, you know, Lewis structures are something that a lot of y'all still are not very comfortable with, but realize that Lewis structures have a huge impact on acid and base activity, such as if you look at dimethylamine, right? Dimethylamine is essentially this is the base itself, right? From a structural perspective. Around the nitrogen, what is the molecular geometry? So around the nitrogen, the geometry is trigonal pyramidal, 3 with a lone pair, right? We have a tetrahedral geometry around both carbons, okay? Now, what do we know about nitrogen as it pertains to polarity? Polar or nonpolar? Most of the time, nitrogen involved with something is going to lead to a polar bond. Electronegativity of nitrogen is greater than carbon and hydrogen, so we end up with polarity towards nitrogen. We end up with a net dipole in that direction, so this would be considered a polar molecule, okay? Now, how does it interact with water? Well, this lone pair here, and because of the polarity, the electronegativity of the nitrogen itself, the hydrogen associated with the water is essentially plucked from the water. So this, what we're seeing in this reaction, not only do I expect you to be able to write this reaction, I need you to understand what's going on. Because when you move forward in organic chemistry, you're going to start getting questions about how structure impacts acidity, particularly organic 1, because I know Pam and I've talked to her about this. Why is it that this, once this hydrogen, has to do with electronegativity? It has to do with General Chemistry 1 concepts. Everything builds off of Gen Chem 1. So nitrogen essentially plugs this guy, leaving you with the conjugate base and leaving you with the new conjugate acid, which is now tetrahedral in geometry and positively charged. Still polar. Still polar. At this point, at this point, a little bit polar, right? Because we have a little bit of symmetry, but we don't really care so much about the polarity as much as we know that it is now a conjugate acid. So it has kind of fulfilled that need, that pull for the positive proton. So that's what's occurring there, just to give you some Lewis structure perspective so that you can understand what's actually happening in solution. So I give you a 2.4 kilograms was dissolved in 6.5 liters of water, determine concentration. So same concept, 2.4 kilograms. So we got 1 kg is equal to 1 times 10 to the 3 grams. 1 mole is equal to so we got 12.01 plus 3.01 times 2 plus 14.01 plus 1.01 should be 45.06. 45.06 grams, and then this is divided by 6.5 liters, and then we get a concentration. So 2.4 e to 3 divided by 45.06 divided by 6.5, and we're dealing with 8.19 mole, extremely concentrated, right? And I'm trying to use these large numbers to make it a little simpler. In a practical, realistic application, a lot of these high molarities are not achievable, right? Because you end up getting to the saturation limit. We talked about saturation of solutions. But mathematically, we still treat this the same. Determine equilibrium expression. Okay, so C, equilibrium expression is now Kb. It's still product over reactants, and we still leave water out. So concentration of the conjugate conjugate acid, NH2 plus times OH minus all over now we have the Kb. The ice table, again, involves B plus water, giving us HB, or BH, however you want to look at it, plus OH minus. So we're dealing with an ice table. That gives us 8.19. We're not worried about water. 0, 0, minus X, 8.19 minus X, plus X, X, X. Exactly like acid, only difference is we're dealing with Kb. And we should represent it as such. Okay? And then part D, in this case, asks us to calculate the pH. And we can only calculate the pH by determining the hydroxide concentration, because the hydroxide concentration can give us POH. So to do so, we need to set up and show that Kb is equal to the value on the reference material, which in this case says 5.1 times 10 to the negative 4. Therefore, 5.1 times 10 to the negative 4 is equal to X times X over 8.19 minus X. We can drop X in this case, so we should have 5.1 times 10 to the negative 4 times 8.19 is equal to x squared, and then we show that x is equal to 0.065. Which means that this is equal to hydroxide which means that the pOH is equal to negative log of this value, 0.065, and the pOH 1.19. Therefore, the pH is equal to 14 minus 1.19, which is equal to 12.81, excuse me. Which is basic. A lot of people are going to solve this, get this value, know that it's concentration of hydroxide, and then give me the pH is 1.19. But you should recognize you're dealing with a base, you should expect a basic pH. So we have a pH of 12.81, above 7 is basic. All we had to do was go pOH to pH with this relationship. You can also use the auto-ionization constant of water, Kw, to solve for hydroxide, hydronium ion, and then go from there. There's multiple ways once you get this value of OH. All you need is OH. Any questions about this one? The only difference here, we're dealing with a base, but the process was exactly the same. Drop X, solve for X, apply X. Now, this is all situations where you have been given Ka or Kb and somebody asks you to determine pH, right? So the next example, 5, we're going to do kind of the opposite. We're going to go the opposite direction. All right. Okay. Number 5 says that we have a value of moles of an unknown monoprotic acid dissolved in 3.3 liters. So we know that moles of HA is equal to 7.7 times 10 to the negative 1 moles. So we've been given an amount, we just don't know what we're dealing with, right? We don't know what the acid is. If we don't know what the acid is, then we can't go to our reference materials and get the Ka. They tell us that it's dissolved in 3.3 liters, so we got volume of H2O is equal to 3.3 liters. Therefore, we do know that there's a concentration of HA, which is going to be important for us, 7.7 times 10 to the negative 1 moles over 3.3 liters. Which is, well, 0.233. So we got 0.233 molar. All right, so we know that much even before we have to get started in the question. They tell us the resulting pH is 5.15. So we've also been told that the pH is equal to 5.15. So we know right off the bat that we're dealing with a weak acid, right? Well, we should recognize that we're dealing with a weak acid because strong acids have a high dissociation amount. They pretty much acidify most of your aqueous solutions to very, very low acidity values, low pHs, right? High acidity, low pH. And then they ask us to determine Ka and then ask, is it a weak or strong? Well, when we're talking reaction, when we're dealing with a generic, we should write the generic acid-base reaction. HA plus water, equilibrium with hydronium plus conjugate base. Again, what is the conjugate acid? What is the conjugate base? It's just going to take the labeling it every time. Just go ahead and label it even if it doesn't ask you, just so that you get comfortable. All right? Equilibrium expression for this, again, is the generic Ka is equal to H3O plus times A minus all over HA. And the ice table. So I'm going to do the ice table here. We know water is nowhere to be found. Now, we do have the initial concentration, 0.233, but we do not know the equilibrium. We do know the change. Change is going to be minus x. We do know 233 minus x. We don't know the value here because we have to determine the value of x here. So we know this is plus x. We know this is plus x. We know this is x and x. This is our generic form. But if we haven't been given a Ka, we can't solve to find Ka without having x. So how can we deduce x?
pH.
Right, we have to use the pH to find x. This is where this kind of question, I imagine the majority of people, if you were not given direct instructions, people would be like, I don't know what to do. This is going to be the roadblock for the majority of y'all on assessment time. You have to be able to apply knowledge. If the pH is the negative log of the hydronium concentration, and you've been given the pH, you can mathematically then calculate hydronium concentration of the solution, assuming that the solution has reached equilibrium, and that way you can solve for x. Once you solve for x, you can then solve for Ka. So if you know pH is 5.15, and you know that negative log of hydronium is equal to 5.15, then you know that the concentration of hydronium is equal to 10 raised to the negative 5.15. Then you'll see that hydronium concentration is equal to 7.07 times 10 to the negative 6. Again, just mathematical manipulation. Gen Chem 1. This is all Gen Chem 1 right here, the pH stuff. Okay, now that we know H3O plus, we now know X. This is equal to X. Has to be, because we know the pH. Now, if we want to talk about this kinetically, right, if we go back into kinetics, the equilibrium for these acids dissolve, the kinetics is so fast that we don't have to wait, right? We don't have to wait very long. So it's not a slow process, it's a very fast process from an equilibrium standpoint. Now we're doing the math on equilibrium, but to apply it back to what we've learned before. Okay, here we're dealing with X, 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 and if we look at X in this case, Ka is equal to then X squared over 0.233 minus X. And if we solve this appropriately, and you don't have to drop X, right? But if you do drop X and you don't drop X, you'll see that the values are going to be pretty similar here. So 7.07 e to the negative 6 squared divided by 0.233 minus 7.07 e to the negative 6 gives you 2.15 times 10 to the negative 10. And we see that that is an extremely weak acid, right? Anything times 10 to the negative 10 is extremely weak, and it doesn't look like we have one that is comparable to that on our table. But here is the Kf unknown. So this is taking pH and amount and calculating Ka. Again, you need to know initial concentration. You can either be given an initial concentration. In this case, I asked you to calculate it when you have been given a number of moles. So here is an example of Ka. Any questions up until this point, and I'm going to start talking some new material that's in a little bit of it's in the PowerPoint. Talk about salts, a little bit about salts and their impact on acids. This is essentially monoprotic acid base, and this is what you need to know about that. Anything, before I get started, new material over, anything on the video lecture that was unclear, that you might want some extra work with, or anything on these style problems that are setting up equilibrium and solving for them. Now will be the time to ask those before we move on.
No, I figured it out.
All right. Okay. Let's take a look at some of the slides that are later on in this particular lecture. Yeah, 16 is just such a big chapter to try to cover it all in one shot, so that's why I kind of wanted to utilize that video lecture as in conjugate with this, in conjunction. And again, percent dissociation would be that over the whole. Let's see. Okay. Should be. Now, your list of strong acids, you need to know those, right? You need to know those. List of strong bases, you need to know those. They go through all of this, which is what we talked about. Now, we won't do so much with the polyprotic acids, but I wanted to just quickly talk about your polyprotic acids such as phosphoric and sulfuric, and I think they give you a couple other citric is a good one. Citric, right? We all love our orange juice. So generally speaking, we list sulfuric and phosphoric as kind of strong acids, but if we notice that your K's for each of those are fairly big, right? I think they list those as the strong. So sulfuric is listed, not phosphoric, excuse me. But when you're given these values, each individual dissociation has its own K. And hopefully people, kind of understand this. That each of these processes, if you were to have phosphoric acid or H2PO4 or HPO4 or PO4, each one of these has its own Ka. So they call this Ka1, Ka2, Ka3. I don't so much focus on calculations involving these. We'll talk about calculations involving these in chapter 17 a little bit more. But I mean, it's just so much to talk about. And from a computational standpoint, this is kind of beyond the scope of this class. When you get into analytical chemistry, you will talk a little bit more about multi or polyprotic acids. But the pH generally depends only on the first dissociation, because all of the dissociations after that, if you notice, those values of Ka become much, much smaller, which means it's a lot less likely for it to happen after the first dissociation. Okay, we talked about bases and Ka, Kb. Now this is where I wanted to discuss today a little bit about the acid-base properties of salts. So when we're dealing with salts, a lot of ions can actually react with water to create hydronium or hydroxide. And we call this hydrolysis. To be able to determine whether it's an acid or a base though, you have to look at the cation and anion separately. You can see situations where the cation can be acidic or neutral, or the anion can be acidic, basic, or neutral. So, if you're dealing with the anion of a strong acid, so let's look at two examples. HCl, HBr. If we look at the dissociation of each of these, we end up with hydronium plus chloride, and for bromine, hydrobromic acid, we end up with hydronium and bromide. Now, because each of these not only are acids, but these are strong acids, the conjugate here, chloride and bromide in solution, are both neutral. Means that their interaction with water is not electronegative enough, essentially. Their identity is not electronegative enough to pluck that H. Remember we talked about plucking the H. If you look at bromide, we're dealing with 8 electrons in the valence, and if we're looking at water, bromide is not going to pull the water, right? Game ain't strong enough, money ain't long enough. So therefore it is neutral. It's not strong enough to get H away from O. Okay? Neither is chloride. So there is no reaction, therefore we do not get a conjugate again, right? Sometimes that occurs. Now, let's talk about this in terms of a salt. So, if we were dealing with a salt, we would have to be dealing with something along the lines of, let's say, sodium chloride or sodium bromide, right? Then what would occur is we would mix with water and we would end up getting the dissociation of these two. And we already know that the chloride and the bromide are neutral, right? But what about sodium? So, we'll have to talk about sodium when we get into cations. Now, if we know those anions are neutral, let's talk about the anions that are not neutral. The anions are weak acids. So, in the case of propionic, which we were just using, C3H5O2, C3H5O2, when that reacts with water and creates C3H5O2 minus plus H3O plus, we now again have a weak acid, or Wa. We have water, which is the base in this particular case. We have the conjugate base and the conjugate acid. This is an anion, but however, this anion is no longer neutral, it is basic. Now, why is that? And this is where foundational understanding of equilibrium has to come into play. If equilibrium says that there is a reverse and a forward reaction occurring at the same time, that means that there is an amount of your conjugate that is interacting with hydronium to reform your acid. This is a process that's occurring back and forth, back and forth, back and forth. So, for this to occur back and forth, it has to have some basic quality. It has to act as a base. So, anions of weak acids are conjugate bases. They create hydroxide in solution if they encounter water. So what that means is that subsequent to this, outside of this equilibrium that's occurring, you also have C3H5O2 minus that's interacting with water to form hydroxide and the original acid. So, without talking about the polyprotic stuff, when we're just talking about salts and we're talking about conjugate bases, the salts of these can give us non-neutral and basic properties. So, for example, what if I gave you sodium propionate, right? If I gave you sodium propionate, it would be neutral, excuse me, and we had this aqueous, then it would dissociate into sodium plus C3H5O2. And if I was to ask you, once sodium propionate was dissolved in water, would you expect the salt to behave as a base or an acid? Okay? Right now, when we're looking specifically at the anion, we're going to see this as a conjugate base. We know it's a base because it's the conjugate of this acid. So it's going to have basic properties in solution. And once I get through this, we'll do a couple of full examples and talk about how this can be calculated. But hopefully we see that if it is a conjugate base of a weak acid, meaning can you go to your reference material, look up the structure, that salt is a conjugate of a weak acid, so it should be basic. That's all I'm asking you to do here. That's all I'm asking you to do here. But that's anions. We now have to talk about the cations, sodium, and other cations, other metals in solution. Okay? Metals, however, have a little bit different set of rules. Group 1 or 2 metal cations are neutral. Meaning, sodium, neutral. Potassium, magnesium, calcium, all neutral. So, since both of these are neutral, what do we expect to happen to the pH once we dissolve sodium chloride and bromide? They're neutral. Nothing. We should expect nothing. Right, so in the question, when I give a list of questions, what do you expect to happen to the pH when you dissolve sodium chloride or bromide? You have to say nothing. Now, what about if you dissolve sodium cyanide in water? We should expect sodium plus. How do we know that this is going to impact our pH? Neutral. What about cyanide? Should be basic. Why? The conjugate base of HCN, which is on your list. Which is on your list. So, therefore, once this is dissolved, what occurs? CN minus plus water to create HCN plus OH minus, and we have this solution, which we just talked about how to solve in these scenarios. So if I was to give you that you dissolve a kilogram of sodium cyanide, what is the solution pH? You have to recognize that this is a conjugate base. You have to then apply that, put that into a chemical reaction, and then calculate using the simple stuff that we did at the beginning. But this is where the application of the knowledge comes from. But here, since cyanide is a pretty strong base because the acid is very, very weak, then we should expect this to have somewhat of a basic pH above 7. Okay, so the cation in this case did not impact pH, but the anion did because it was a conjugate base. Now, we're not going to talk much about polyatomic right now, but transition and post-transition metals are acidic. And the question is, why? Question is, why? So, when you talk about transition and post-transition, we're talking about the iron 2+, iron 3+, manganese 4+, etc. And if you look down at the bottom, they show you zinc, aluminum, both give acidic pHs. What ends up happening is something called hydrated cations. So transition and post-transition metal form a hydrated cation. The water attached to the metal is more acidic, making the hydrated ions acidic. Now, what does that look like? Again, it goes back to transition metals and how they interact. I will say that most of you all don't have much experience with this. We're going to talk about this in the transition metal chapter a little more in depth, but for simplicity purposes, what essentially happens is you end up with a structure, and they use iron in this case. Iron 2+ creates a octahedral interaction with water that involves, if we remember, octahedral means 6 things are connected to it, right? And what ends up happening is because iron is positively charged, the oxygen in water, which has a negative partial charge due to molecular geometry and polarity, the oxygen ends up attracted and now, hopefully, this is the beauty of Gen Chem 1 if you really brought those concepts with you. Now, if you remember that if the polarity or the electron density is closer to oxygen, and a positively charged metal is pulling that electron density in really strongly, then the electron density is moved even further away from these hydrogens, which make these hydrogens even less held on to tightly. So these hydrogens become more acidic because of this red interaction that I'm showing. And that is due to electron density, polarity, understanding molecular geometry, right? So essentially, oxygen is paying attention to iron, and H can just scoot on away, right? H can just run off a little bit easier. So there is a Ka associated with transition metals here. So if you have a soluble salt that involves transition metal or a post-transition metal, then you end up with this scenario occurring in solution, and you end up with a more acidic situation. So what does that look like over here? Let's say that we were trying to dissolve, they use nickel. Let's say we had nickel chloride plus water. In solution, we are going to create nickel 2 aqueous, and we're going to create 2 chloride ions aqueous. What do we know about chloride? It is the conjugate of a strong acid, therefore neutral, will not impact our pH. Nickel 2+, however, transition metal or post-transition metal, has acidic character. Therefore, in solution, right, we would see nickel 2 plus interacting with H2O to create H3O plus the hydroxide, which they're showing here as essentially as octahedral. Now, I'm not sure if nickel is octahedral, so I'm going to just write it that way. And they're going to show this as nickel. A complex is what it's supposed to be listed as, H2O 5OH. And this should then have a +1 charge where this has a 2+ charge. Because yeah, they used iron 3+ there, either way. Now, I wouldn't be asking you to do this because, right, this is transition metal complex. This is some stuff that's later on. But generically speaking, you need to recognize that this salt would create an acidic solution. That's what I'm asking you to do for purposes of this chapter. I'm not going to ask you to write all of this, but this is to show you kind of what is occurring. Now, why would the hydroxide be attracted to the nickel? Positively charged, right? Positive and negative are going to interact. But it's good to know that. Now, if you have a metal cation that is neutral and an anion or a strong acid, you're neutral. If you have a metal cation with an anion of a weak acid, you're basic. We showed that example. If you have a transition with or a polyatomic cation with the anion of strong acid, it's acidic. And if you have a metal cation and a polyatomic anion, then you have to compare Ka and Kb. So the last example is what happens when you have the transition metal along with something that is, so let's say we did have iron 3, let's say we had iron 3, C2H3O2, iron 3 acetate. So, if we got iron 3 acetate, we're dealing with a salt that involves a cation that we know is acidic and an anion that we know is a conjugate of a weak acid. So we know that it is basic, right? So we have something that is acidic and something that's basic. Now, how we determine the outcome of the solution has to do with Ka and Kb of each of these. So we got to look at both of these. So we have to look at the Ka of iron and the Kb of acetate. And if we look at Kb of acetate, to get Kb of acetate, we need 1 e to the negative 14 divided by 1.7 e to the negative 5. So we got 5.88 e to the negative 10. Now, and quickly, hopefully we saw this already, but remember, Ka times Kb is always equal to Kw. So this is how you can manipulate in between the two. You got to remember that. So what I did here is I took Kw and divided it by the Ka for acetic acid. That's how I came up with this value. Now, if we look at the Ka of iron, 3 plus 6.3 times 10 to the negative 3. Therefore, we see that iron dictates whether it is acidic or basic in this solution. So even though stoichiometrically, and I should have a 3 right here, even though stoichiometrically acetate is more of it in solution when it dissolves, we are not dealing with a basic solution once iron is dissolved, because it is effectively a stronger acid. So that is the salt solution. As it pertains to strength, strength has to do with molecular geometry. I'm not going to talk so much about that, I'm more interested in you understanding and getting the ability to answer these questions. So now let's talk a little bit about examples of questions that involve these salts. I think I found a couple of them in the text, so I didn't have to necessarily write it. All right, I like this one. Let's go here. Okay, I like 16.110. So this is 16.110 in the text. Just before we get into heavy math stuff, arrange the following in order of increasing acidity. So we got NH4, NO3, NaNO3, CH3COO, NH4, sodium fluoride, NaF, and CH3COO, Na. All right. So this is a great type of question. This goes to exactly what I said. Can you deduce and rank these based upon what they are made out of? Now, I will go ahead and tell you that CH3COOH, you may see these two listed similarly, but CH3COO is the same as C2H3O2. I'm gonna try to keep these consistent with what's in the reference material so that I don't want you to get confused here and be like, I don't know what that is. These are both acetate. But for purposes moving forward, when I give you these salts, I'm gonna try to structure them on my assessments as they are structured in the equilibrium constant, so that way you can go and determine them. So we're dealing with the first one, which is NH4NO3. So we're dealing with ammonium and nitrate. So unfortunately, I wish I could ask these questions of you using nomenclature, but I think everybody will fail, unfortunately, even though you're supposed to know this from General Chemistry 1. Ammonium nitrate. So we have ammonium, we have nitrate. Ammonium is what? It's basic, right? We know it's a base. We know it's a base, but it's also the conjugate base of an acid, right? NH4, is the conjugate acid of a base. Don't get confused. I'm trying to move too fast. Ammonium is acidic. It is the conjugate acid of a base that is on our reference materials, NH3. So what is NH4? NH4 is NH3 plus water to create NH4 plus OH. Remember, BH plus. That should give you that. Polyatomic cations are acidic. Okay, you need to go to your reference to determine that. So we got a conjugate acid. So we do have some level of acidity. What about nitrate? nitrate is a conjugate base. It's a conjugate base of a strong acid, nitric acid, HNO3, therefore neutral. You have to be able to recognize conjugate. That's why I said get in the habit of just writing conjugate acid, conjugate base. So, as far as it pertains to acidity, we do expect this to be acidic. And what dictates its acidity? But what? Specifically, the Ka of NH4 is how we're going to be able to rank this. Just looking at it doesn't tell us. We need to know the numerical values, and those come from the reference materials. Okay, let's take a look at sodium nitrate. Sodium nitrate simple one, these are both neutral. Both neutral. So we shouldn't expect it to be acidic, we should expect it to be neutral. All right, now we have ammonium acetate, and I'm going to keep ammonium in the front just because we're starting, trying to keep it consistent. Ammonium and then acetate, CH3COO negative. Now, we already said ammonium is the conjugate acid, is acidic. Now, what about acetate? We have a conjugate base of a weak acid, so we should expect it to be, it is a conjugate base, so we should expect this to be basic, we should expect this to be acidic. Now, as it pertains to here, this salt can go both ways. But what decides if this is acidic or basic? We have to compare, in this case, Ka and Kb for these two. And if we look at the Kb, the Ka for NH4, we take 1e to the negative 14 divided by Kb for ammonia, 1.8 e to the negative 5, and we end up with 5.5 e to the negative 10, 5.6 e to the negative 10, and Kb for acetate is 1 e to the negative 14 divided by acetic acid is Ka, 1.7 e to the negative 5. 5.88 or 5.9 e to the negative 10. So, from a magnitude perspective, acetate is a stronger base than ammonia. Ammonium is an acid, therefore, we should expect this to be basic. Calculating Ka and Kb from a Ka or Kb is a direct calculation using Kw. You got to be able to do that too. All right. Lastly, the last two, sodium and fluoride. Sodium we know is neutral. Pretty much you can go ahead and just chalk that off. Neutral. But what about fluoride? Fluoride is the conjugate base of what acid? HF is a weak acid. HF is on our list. Look on your list. If it's on your list, it ain't strong unless it says it is, right? So HF is the conjugate base of a weak acid. It is basic. Therefore, this should also be basic. And if you looked at the Kb for F minus, the Kb for F minus is 1 e to the negative 14 divided by 6.8 e to the negative 4, 1.47 e to the negative 11, 1.5 e to the negative 11. Now, is it more or less basic than acetate? Comparing numbers. It's less, right. This is less basic than acetate. And then we go to our last one. So then we can rank them. I love this question. You might see one like this. CH3COO. Well, let's keep it in check. CH3COO minus and Na plus. We know sodium is neutral. And we know acetate is basic because it is the conjugate base of a weak acid. And we know that the Kb here is equal to 5.9 e to the negative 10. Okay, so we know that we have three that are basic, one that is neutral, one that is acidic, and the question asks us to rank them in order of increasing acidity. Increasing acidity. Okay, so we need to know which one is the most basic. Which one is the most basic? So out of these three, we have one salt that is acidic and basic. Together, we have two salts that are neutral and basic. So the most basic is going to be this guy, sodium acetate. The reason for that is because we have a Kb that is larger than the Kb for another neutral cation, right? So we should have this, which is larger than that. So increasing acidity should be sodium acetate first. Then, the basicity here is more than this, but this one is more because we don't have any acid in solution either. Hopefully you see that this has two in solution, both of them roughly about the same. So this one would be next, ammonium acetate, and then sodium fluoride, because this is less basic, so it's more neutral. Then we're dealing with our neutral salt, sodium nitrate, and then our only acidic salt, NH4NO3. That's a great question, because it applies understanding and being able to relate Ka to Kb. Now, again, the most questions you're going to have is why is this one and this one, how do we rank these two? The reason I rank this one as more basic is because we have a neutral cation. Here, we had a non-neutral cation. We had an acidic cation. So you should expect this to be less basic or more acidic than this one because of that. But here's your ranking. Any questions about that one? And I like that kind of question. All right, let's see if they have another. I want to do one that is salt with a calculation involved. And I may be able to just develop one. I'll just write one out here now. All right. And we'll use one of the ones that we haven't used yet. And apply this to one of the large scale questions, more along the speed, I guess, of what I like. So let's look at Let's look at Clorox. So Clorox is made of sodium hypochlorite. And let's say that you had a (6.3 times 10 to the negative 3 molar solution. And I ask you to determine the pH. Now, sodium is neutral. Hypochlorite is the conjugate of a weak acid. Most people's mistake or problem here is they're going to be like, sodium hypochlorite is not on my list, right? This is not on the equilibrium constant list. What you have to be able to recognize is that hypochlorite is the conjugate of hypochlorous acid and there you have the reaction that you need to be able to write. Once you get to this reaction, everything from there, easy peasy. So once you have the reaction, you can write the ice table. Once you have the ice table, you can plug in 6.3 e to negative 3. We're not worried about water. 0, 0, plus x, x, minus x, 6.3 e to negative 3, minus x, and then Ka is equal to. So I did this on purpose to show you something is wrong, because this is what a lot of people are going to do. Why is this wrong? I have asked you for the pH for the solution, right? Mm-hmm. We have decided that we can determine that, and we should be able to determine that hypochlorite is, in fact, something that will impact the pH. But what's wrong with the setup in the ice table? Because this is what I see a lot of people do. Okay, let's go back to the very beginning. We have a salt, right? What do we expect for sodium to do? Nothing. Neutral. What do we expect hypochlorite anion to do? Should impact it because it is a conjugate base. This should create a solution that is basic. Why does it create a solution that's basic? What does it do in solution? Right, produce OH. It's the wrong reaction. This is a reaction of hypochlorous acid with water. But I gave you a situation of hypochlorite in water. So we should be creating the acid in this example, right? So a lot of people are not going to make that distinction. That's why I wanted to use a simple example first. We need to be creating an acid, producing hydroxide. How do we know we should be producing hydroxide? Because we should recognize that this should give us a basic solution. Why? Because this is the conjugate base of a weak acid. Where can we get that information? Reference. This is why I'm a big utilizer of reference material. So now we have it written correctly. Now we also do not have a Ka. This equilibrium expression should be denoted as Kb. Why? Because we got a base. We are creating hydroxide. Once we plug this in, we see that Kb is equal to x squared over 6.3 e to the negative 3 minus x. But if you go to the table, if you plug in this Ka number, it's going to be wrong. A lot of people are going to plug in Ka right here. We do not have the Kb for hypochlorite, excuse me. We do have the Ka for hypochlorous acid, so therefore to get the Kb, we have to divide Kw by Ka. And that is 1e to negative 14 divided by reference material, 3.5 times 10 to the 8. 10 to the negative 8, excuse me. So Kb is equal to 2.86 or 2.9 e to the negative 7. So now we can plug this value into this equation and solve for x. We can also drop x here if we want to. How do we know that? Well, we can divide we can divide 6.3 e to the negative 3 divided by our Kb value, 2.9 e to the negative 7, and we see that we get 21,000. So we can technically drop x here. We end up with then x squared equals 2.9 e to the negative 7 times 6.3 e to the negative 3. Therefore, x is equal to the square root of whatever that number is. 2.9 e to the negative 7 times 6.3 e to the negative 3. Square root, second answer. 4.3 e to the negative 5. So that should be 1.827 e to the 9. 1.827 e to the negative 9. So x is equal to 4.27 e to the negative 5. Now, this value is now equal to OH minus concentration, which can then be calculated using POH. So the POH is negative log of this value, 4.37. And therefore pH is equal to 14 minus this, so we should be dealing with 9.63. Great question. And looks simple, right? Looks simple. I didn't even ask you to calculate all the concentration stuff up front. But you have to make sure that you don't end up making any pitfalls to get to that point. So we went all the way from salt dissolved and how that will impact pH. Conjugate acid, conjugate base, we need to still be able to label these, right? This is the conjugate acid, this is the conjugate base. Water is in fact the acid here. Hypochlorite is the base. Because it is a salt and it is an anion of a weak acid, or the conjugate of a weak acid, we should expect it to be basic, and when we do the calculation, we see that it is slightly basic at 9.63. Okay, we'll do one more, and I'm gonna try to make this one, make you kind of do some calculation on the back end. Any questions about this? Any concerns calculation-wise? Remember, you can drop x here because the relationship between this number and this number. Okay. Let me let's talk about a multi-part. What mass of HF was dissolved in 0.25 liters of water if the pH of the solution is 4.03. What mass of ammonium chloride should be dissolved in a separate solution .25 liters of water to achieve same pH? Possible? Okay, so first part of this problem, I want you to convince yourself that you can do that on your own really quickly. Not quickly, but it should be pretty straightforward. I'm giving you the acid you're using, I'm giving you the volume, I'm giving you the pH, right? And then the second part of the question, which kind of incorporates a little bit of what we talked about today, is a salt, and can you, using that salt, achieve a pH that is the same in the same amount of solvent? So I would convince myself that you can do that, and then we'll go through that. At least get it started. Also, while you're working, before we get up out of here, I wanted to say that I have uploaded a take-home quiz. Not mandatory. You can do it if you want to. That take-home quiz, you get, I think, until Thursday night to do it. You can use whatever resources that you would like. It will be graded if you submit it and add it to your quiz grades. It will be just another quiz, add it into the quiz grades. If you do not do it, it will not go against you, but it's another opportunity for you to add to the quiz grades. I gave a take-home quiz in the other 1412 course, so I wanted to make sure that it was fair, and I was offering you all this, the same one. So it's underneath this module and take-home quiz, and then there's a drop box. So you just use scanner, scan that in. I think it's 2 pages. A little bit more involved, obviously, than the in-class assessments. So it might take you a little while. And again, that is on equilibrium, not acid-base stuff. Acid-base, we'll have a quiz on this stuff next week. Again, as always for this first part, you always want to be able to make sure that you write the reaction correctly. First part, second part, equilibrium expression. Third part, do the math after that. Again, you should be using pH to calculate hydronium to then utilize that value in equilibrium in the ice table. So if you know the hydronium, you then know what you can then solve for the initial concentration. Okay, so you should at least have this point, because we run out of time. I'll go ahead and walk through this. So you should at least understand this part. You should also understand that because we are dealing with a weak acid, right? Generally speaking, you're going to see that that X can be dropped from the minus. So you can be dealing with a Ka that's 9.33 e to the negative 5 squared all over concentration of HF. You have Ka, reference materials, you have concentration, 9.33 e to the negative 5, so you can solve for HF. So you can divide that by Ka, which is 6.8 e to the negative 4, and we end up with a concentration of HF that's equal to 1.28 e to the negative 5 molar. We had 0.25 liters. So to get the number of moles here, we can multiply this times 0.25 liters. That will give us the number of moles, 3.2 times 10 to the negative 6 moles of HF. Therefore, to get number of grams, we multiply it by the molar mass, which is 20, right? Because HF is 19. So essentially 20 grams of HF per 1 mole. And therefore we end up with 6.4 times 10 to the negative 5 grams. Or 64 micrograms, right? So it just takes 64 micrograms to shift the pH from 7 down to 4, right? That's very little. But that is a function of Ka, right? So this question involved solving for initial, and we hadn't done that yet, right? We had done mostly is solving for equilibrium, but to solve for the initial takes into consideration the X. Now, let's say you did use the minus X here. You could have done that, and you could have done the question. It still would have came out to the same value, right? Because you would have ended up multiplying minus X. You would have still got some values for that. Okay. Now, for the second part, it goes back to the salt question, right? Salt question asks us what mass of ammonium chloride. We should recognize that chloride ion should be neutral. So it shouldn't have any impact. Ammonium should be acidic because it is the conjugate. Therefore, if we're dealing with 4.03, we essentially have the exact same structure up here, except we have NH4 instead of HF, NH4 instead of HF, and we got NH4 instead of HF. The difference, however, is that the Ka, let me put a positive on all these, the Ka is different. So we will have a different value because we got to look at a different Ka. So now to get the Ka for this, we have to go to Kb for ammonia, and 1e to the negative 14 divided by 1.8 e to the negative 5. So 5.5 e to the negative 10 here. So our Ka for NH4 is 5.5 e to the negative 10. Therefore, we end up with a concentration of NH4 plus is equal to 9.33 e to the negative 5 squared divided by second answer gives us some huge number, 15.67 molar times 0.25 liters gives us number of moles, 3.9192 moles of NH4 plus. And to get that number of moles of NH4 plus from NH4Cl, we have to recognize that you get 1 mole of NH4 plus for every 1 mole of ammonium chloride. And then we know that 1 mole of ammonium chloride is equal to 35.45 plus 14.01 plus 4.04, 53.5 grams. So we end up with 3.92 times 53.5. We end up with 209.72 grams of ammonium chloride. In 250 milliliters. So the next question was, is this possible? It's a lot of grams, right? That's just as many grams pretty much as you have in water. It's going to be tough to get that to dissolve, right? It's going to be tough. So probable, probably not. Possible, I guess so, yeah. But probable, probably not. So it would take so much more. So much more. We had 209, the other one took micrograms, right? Why? And then to wrap this all up, and hopefully if I was to give you a question like this and then ask you to explain it, in a simple explanation, why would it take so much more of this?
Can you repeat the question?
Why would it take so much more of ammonium chloride than hydrofluoric acid to achieve the exact same pH in the solution, in the same amount of water?
Wouldn't it be like soluble?
I'm asking you, why is this number so big? Solubility has to do with what you do with this amount in water. Why is this number so much bigger? Not as strong, right? That's a simple explanation, but simple and specific would be Ka, right? The not as strong, you're referring to Ka. What I'm trying to get you to show is that the Ka of HF is much, much greater than the Ka for NH4. And therefore, we see a much, much larger difference in the amount that's needed, because the two Kas are much, much different. So this is a great question. Which one of these would you it would be more practical to use in a laboratory setting? That would be the way I would frame this question. Which one would be more practical to use? A little bit of HF or 200 grams of salt? And it has to do with Ka. It has to do with K. Because if you look at it, the molar masses are not that much different, right? We don't have huge orders of magnitude difference in the molar mass. But we got huge orders of magnitude difference in the Ka. And that's what changes things. So with any of the acid stuff, I've been dealing with some sound issues. I've been in the process of trying to make a couple more equilibrium videos, but I'm trying to iron out some sound issues, because those of y'all who clicked on a lot of the videos, you've seen some of the videos that have the static stuff, and that stuff is awful. So I'm gonna try to remake and work on some of these videos and change that, but I'm still having static problems with the audio portion. My blue equilibrium constant sheets, let's put those back, because we'll use those next week for the assessment. My reference material, stack those back up. I'll see everybody on Wednesday. On Wednesday, we will talk about